Welcome to the CEAT Research Seminar Series, Virtual Edition.
Good afternoon, everyone. My name is Chuck Bunting. I'm an Associate Dean of Research in the College of Engineering, Architecture, and Technology. Welcome to the CEAT Research Seminar Series, the virtual edition. This is our final talk for talk series for the fall 2020. We look forward to hearing two speakers today. Just a couple of bits of housekeeping, and you'll see it pop up on the screen behind me, is the fact that we are recording today. So that you would want to be on your best behavior, as always. Please post questions to the chat, and if you wish to have, you can also chat with one another as well. But we will save time for questions at the end. So without further ado, we're going to begin with our first speaker today. Prem Bikkina is Associate Professor and Harold Corson Chair in Petroleum Engineering in the School of Chemical Engineering here at OSU. He holds a bachelor's and a master's degree in chemical engineering and a PhD degree in petroleum engineering. He worked as a postdoctoral fellow at Lawrence Berkeley National Lab prior to joining OSU. He also worked at various national and international chemical and petroleum industries. His research work on enhanced hydrocarbon recovery, geological sequestration, and multi-phase separation resulted in many high-impact journal publications and patents. In addition, he's worked on 13 research projects, 10 as PI and 3 as co-PI, sponsored by various government and industrial funding agencies. Dr. Bikkina received the 2016 Outstanding Reviewer Award for the Journal of Environmental Chemical Engineering, the 2016 SPE Mid-Continent Regional Service Award, and the 2017 SPE Distinguished Petroleum Engineering Faculty Award, as well as the 2019 CEAT Excellent Teacher Award. We'll let Dr. Bikkina introduce his topic as we turn the mic over to him. Prem?
Yeah, thank you, Dr. Bunting, for the nice introduction. So, my name is Prem Bikkina. I'm a faculty in the School of Chemical Engineering. Today's talk is on a potential solution for boiling crisis. So here is the outline of the talk. I'm going to quickly introduce the boiling curve. Most of you have seen it, and it is just a refresher. And I'll talk about what is boiling crisis first. And then I'll talk about the state of the boiling enhancement methods and what I am proposing, what is the novelty in our proposal, and with some preliminary results. And I'll conclude the presentation. So boiling curve. This schematic, I just take it from a heat transfer textbook. You might have seen it maybe many times. Basically, this is a typical boiling curve, initially identified by a Japanese scientist in 1934. His name is Shiro Nukiyama. And the curve is basically, a logarithmic plot of delta T excess, which is, when we are boiling a liquid, using a heating source, the delta T axis is defined as the TS, which is the bottom inner wall surface temperature, the highest temperature in the system, where the liquid is in touch with, and minus the Tsat is the boiling point of the liquid. Basically the TS minus Tsat is the driving force for the heat transfer. And the y-axis is the heat flux, which is basically the amount of heat going into the system through unit area per unit time. So as you could see here, the boiling curve is actually divided into 4 regimes: natural convective boiling, nucleate boiling, transition boiling, and film boiling. So in the natural convective boiling, this is about from 0 to about 5 degree delta T excess. 0 is not shown here because it is a logarithmic plot. So boiling happens, without bubble formation, vapor bubble formation. You see here, you got a container with some, let us say, water in it, and it is being heated from below. And the container surface, inner wall surface temperature already reached more than the boiling point of the liquid water, and the liquid pool is already at the 100 degrees Celsius. There is a 3-degree delta C here in this picture, and that is actually causing this heat flux. As the boiling point will not rise, as at a particular pressure, we have a constant boiling point for a pure single phase, single component liquid. The only thing that can change with time is, the TS, the temperature of this container surface. So as that changes, the delta T increases, and then correspondingly the flux increases. So as I said, this is natural convective boiling design, where the vapor bubbles are not going to be forming. What happens is the liquid which is closer to this hottest surface is going to be slightly superheated and becomes lighter, and it goes to the top of the liquid. And the liquid which was at the top is slightly heavier and it comes down. That causes some natural circulation of this liquid and contributes to the boiling. The hot vapors are going to be taken to the surface and leaves the liquid. And at point A here, the first vapor bubble on the hottest surface, which I call it as heating surface, is going to form the vapor bubble. And more vapor bubbles are going to be forming as the delta T increases. What happens is, once the vapor bubbles form, they grow in their size, and then because of the buoyancy, they detach from this surface and travel through this liquid pool, agitating the liquid pool, and leaves the liquid as a vapor in the vapor form. So because now we have that forced convection, which is much stronger in terms of its heat transfer capacity, there is a significant increase in the heat flux with a very slight rise in the delta T. The rise in the delta T is an order of magnitude 5 to 30, but you got like 100 times increase in the flux because of that nucleate boiling design. At the highest heat flux, which we denoted by this point C, what happens is you got like most of the this heating surface is actually generating vapor bubbles and occupied by the vapor bubbles. And at that time, the vapor bubbles, basically they are resistance for further heat transfer. They create resistance for further heat transfer, because vapor is a bad conductor, heat conductor. So, and hence, irrespective of the fact that the heat flux, the delta T actually increases an order of magnitude from 30 to 120, the flux actually decreased 2 orders of magnitude. In fact, it has to increase, but because of that vapor bubble formation and layer formation, the heat transfer became so bad. And then to go to the critical heat flux level, again, we need to actually have a delta T more than 1000 degrees Celsius, to this level. From this point where, the heating surface is completely occupied by the vapor and separating the liquid touching the heating surface, heat transfer mechanism is going to be radiation. As radiation is not that effective heat transfer mechanism compared to conduction and convection. That is the reason why we have to spend very high levels of energy to go to the same level of heat flux that we were just able to get with just 30 degrees delta T. So the drop in the heat flux, irrespective of the fact from in the increase in the delta T excess, is called as boiling crisis. This is a natural phenomena. It occurs, and obviously it's not a good thing for boiling heat transfer. So this study is basically to deal with this natural phenomena, to basically prevent it. As there are multitude of applications, all the way from thermal power generation to thermal management in refrigeration and electronics, automobiles, metallurgy, and so on, and various other natural household and industrial processes that involves boiling. It's a very, very important process, that has various applications, and but it suffers with that boiling crisis. And currently there are many state-of-the-art techniques used to basically manage that boiling crisis. Of them, micro and nanostructured surfaces, basically making the heating surface having some micro and nanostructures, uh, you know, are known to improve the heat flux. You know, Likewise, making the heating surface biphilic, meaning that a part of the heating surface is wettable, like with the liquid, and the remaining part is non-wetting surface. Biphilic surfaces are also known to improve the heat flux. And the third one is nanofluids, adding some nanoparticles to the liquid that should be heated or boiled, uh, was also known to actually improve the heat flux. And as I said, these methods, they improve the critical heat flux either by increasing the effective heat transfer area, or improving the wetting characteristics, and or capillary wicking. But the issue with these methods is that they are difficult and are too expensive to make and maintain for practical applications. And moreover, they may not actually completely eliminate the boiling crisis. So what I'm proposing, basically, what is the reason for the boiling crisis? The reason is formation of the continuous vapor layer on the heating surface, right? So can we prevent the, can we stop forming the vapor bubbles on the heating surface? If at all, if we are able to stop it forming the vapor bubbles on the heating surface, is it a good thing? Maybe or maybe not. So when I say maybe, because if we are able to stop the formation of the vapor bubbles on the heating surface, we are not creating the resistance. However, if we don't allow the bubbles to form, what happens is we are still in the convective boiling regime, which is very inefficient in terms of heat flux, very low heat flux. So we need bubbles, but we don't need them on the heating surface. We should have bubbles somewhere else. That somewhere else would obviously be a colder surface, or colder place, because the idea is to prevent a boiling vapor bubble formation on the hottest surface and promote them at a colder temperature, meaning that a physical separation of heating and boiling surfaces. So far, everywhere in the world, the heating and boiling surfaces are the same. They are not separate. Wherever we have that heating, the bubbles form there only. But for the first time, we propose separation of these heating and boiling surfaces, and making the heating surface liquid-philic to prevent the formation of vapor bubbles, and making the boiling surface liquid-phobic in order to promote bubble nucleation at a very low wall superheat. That is the idea behind this work. And the preliminary results, as I said, we have two different surfaces: heating surface, where the heat transfer happens from outside to the liquid, and the boiling surface. We make the heating surface, as I said, hydrophilic. What you're seeing here is a droplet of water on a clean glass surface, making a contact angle much less, less than 30 degrees, which is hydrophilic. And the same surface is actually treated with some hydrophobic materials, in-house treatment methods, to make it hydrophobic. The water droplet is actually beading up with 115 degrees contact angle. So this is going to be our boiling surface, and this is going to be our heating surface. The corresponding surface roughnesses, atomic force microscopy images can be seen here. The process did not really cause any significant roughness. They are pretty similar. So to basically test that hypothesis, separating the heating and boiling surfaces and preventing formation of bubbles on the heating surface and promote the bubbles on the boiling surface. We conducted 4 different types of pool boiling experiments. In the configuration 1, what we did is we have a hydrophilic glass vial filled with water, degassed, deionized water, and inserted a hydrophobic rod. This hydrophobic rod is not heated. It is only heated through that liquid. This whole thing is put on a heater. Heater is at the bottom of the this container, and the heater was set at 200 degrees Celsius, which is good enough to go to that film boiling regime. So, and the liquid is slowly started heating, and then as you could see, when the temperature reaches close to the boiling point of the liquid, the bubbles actually started forming on the rod only. The vapor bubbles are not forming anywhere else. In fact, they have to form here because this is the hottest surface, and this surface is the coldest surface, but the bubbles are forming on the coldest surface and not forming on the hottest surface, going against to the nature. And the bubbles grown bigger, larger with as time progresses, and then the steam at a very high rate, the steam is being generated, and after some time, there was a significant amount of water boiled. So during the entire process, we have not seen a single vapor bubble formed on the hottest surface. All the bubbles were formed here. I have a quick video to show you. Hopefully it's going to play. Just a minute. Video. Okay. Where's that? All right. So I hope you're seeing this, screen, like with that container with some water inside and the hydrophobic rod immersed, and the heat. This white thing that you're seeing is the heater, and it is being heated, and it's a big video. But what I'm going to do is I'm going to just drag it to different locations so you can see the formation of the bubbles. Time. Yeah, you can see that the bubbles started forming only on the rod. No bubbles are formed on the heating surface, only on the boiling surface. And then, yeah, they're growing bigger, only there. Yeah, I'm actually heating here, but the bubbles are forming there. See, like very vigorous boiling is happening on the hydrophobic rod, which is at the coldest, temperature basically. Very vigorous boiling. My camera cannot even capture the rate of bubble, formation after some time. See that? It's very fast boiling. Okay. So coming back to the presentation, that was the first configuration, right? The second configuration is that we did not have the hydrophobic rod in the liquid at the beginning. We let this water boil, or reach the boiling temperature or close to the boiling temperature, and then we introduced this cold rod. This rod was at the room temperature, 25 degrees Celsius. But upon touching this liquid, which is at the boiling temperature, immediate catastrophic, bubble formation, vapor bubble formation, as it is dipped down, more and more bubbles are forming and at a very high rate, only on that surface, not anywhere else. You could see that. This is the boiling surface, coldest surface, heating surface, the hottest surface where the bubbles are not forming. Again, so I have another video to show you quickly, and this is the second video, 2640. So yeah, the heating started, let me take it to 2640. Until then, there was no rod. At about 2640, the rod was introduced. Yeah, look at it. Yeah, immediately upon touching, introducing the rod, you see that, bubbles are forming. And if the rod is taken out, the bubbles are getting stopped. See that? In fact, the temperature difference between that rod and the water is actually negative in this case. Even at that, with that negative temperature difference, the bubbles are forming very vigorously. And so let me come back to the presentation. And that was the second configuration. The third configuration is that, we have, same hydrophilic vial. And instead of the rod, we actually have a glass bead, hydrophobic bead, floating on the surface of the water, which is the extreme case, basically. I'm heating at the bottom, expecting bubbles to form on the bead only on the surface, at the surface. As you could see, the bead, as expected, the bubbles are actually forming only on that bead. Significant boiling happened without a single vapor bubble formed on the hottest surface. And the fourth configuration is that, similar to the previous one, but we did not have the bead floating on the heating, liquid from the beginning. We let the convective boiling to happen first, and then we introduced the bead. Upon introducing the bead, there was a catastrophic bubble nucleation. It was about to fall down because the bead is actually heavier than the liquid, but it was able to float because it is hydrophobic. So then, the vapor bubbles put that bead back up on the surface, and the nucleation continued. And then occasionally the bead was falling down, where it was generating more and more bubbles, and the bubbles were actually taking the bead back up and putting it on the liquid surface. The bubbles were acting like a parachute, creating some buoyant force. And we tested 4 different configurations. In all the configurations, it was proved that the nucleate boiling can be spatially controlled by manipulating the wetting states of heating and boiling surfaces, which has never been done before by anyone in the world. In other words, nucleate boiling can be suppressed where it is not required and promoted where it is required. And in the case of boiling heat transfer, it would be beneficial to suppress the nucleate boiling at the heating surface in order to prevent the formation of the continuous vapor layer, and promote them at the boiling surface to prevent the superheating at the heating surface. Meaning that if we don't have the boiling surface, what happens is the liquid will be superheated because there is a lot of heat coming in, but heat is not going out at the same rate. The liquid will be superheated, and at some point it will be flashed, which is not a good thing. It's not safe. So, okay, finally, I would like to acknowledge, the funding sources, the OSU TBDP, ACS Petroleum Research Funding, and the US Department of Interior Bureau of Reclamation, and the Nitrolake Technologies LLC to support this preliminary research. And currently it is actually, we have 2 active research projects to take it to the next level. And of course, my collaborator, Dr. Khalid Salam, we closely work with with our graduate students, Shobhan Pradhan and Elo and Wa, to actually take this preliminary concept to the next level. And thank you. And any questions are welcome.
Good.
I'm glad that
thank you very much, and I'll applaud for everyone who is muted. If we were together, of course, there would be a very nice applause for this. Thank you for sharing, Prem. I would invite the audience to please go ahead and unmute your cameras. I'm gonna stop for now the participants sharing. I would invite questions at this time for the speaker.
Yeah, please feel free.
Yeah. I can start if you want.
Okay, yeah, please.
I'm familiar with the work, but I really love the presentation. So thank you, Prem, for doing a great job. What I'm not familiar with, and what I would like you to elaborate on, is how durable is the surface treatment, and is there any danger that surface treatment deteriorate over the the lifespan of, say, the boiler, or is it like permanent surface treatment that basically are gonna be very durable for us?
I mean, yeah, the thing is actually, it's not the coating that is actually doing the magic. It is actually the surface wetting nature. So of course, if it is a coating, probably, with time and with maybe, exposure to, higher temperatures may actually deteriorate and probably may not function as we want. However, we don't even need to use any coatings. We can actually make, we choose an inherently hydrophobic material, an inherently hydrophilic material, so that no coatings are involved, there shouldn't be any problem.
Other questions?
Yeah, all of them are muted.
Yeah, I think they can unmute. Everyone is free to unmute themselves. I have a question. Can you discuss what potential implications the success in your area would lead to? Where does this, what's next? Where's this
Yes,
going to go? Who's going to be able to leverage?
That's a very important question, Dr. Bunting. So first of all, by preventing the boiling crisis, what is going to be happening is we will not have the film boiling and transition boiling regimes. The boiling curve, very boiling curve shape is going to change. The boiling curve is, is a pretty accepted, curve in the heat transfer textbooks. First of all, that is going to change. And the second thing is the application. When it comes to applications, for example, nuclear power plants, if we need probably, let us say, a building sized, our engineering north building sized reactor, to produce certain amount of power, if we can prevent this boiling crisis, and probably the size would be significantly reduced to get to obtain the same level of heat flux. And also it's going to be more safer, because we are not, what happens is, if we need to heat the boiling surface, a heating surface more than 1,000 degrees Celsius to get that highest heat flux in the film boiling regime, what happens is, the container surface will melt. Some of the container surfaces will melt, especially it's going to be very dangerous, in the nuclear power plants or thermal power plants.
Very good. We have time for one last question.
Yes. Dr. Hanke joined. Maybe didn't, he was not there before, yeah. Students, any questions? Or Mohammed, any others?
Hearing none, I think we'll move on. Thank you very much. Once again, give our applause through reactions, or the various novel ways that we have to today.